Yes, I forgot it yesterday, didn't know. Ah.
All right, so the last lecture before lunch is the third lecture by Yoshitaka. What is yours?
Right. So before my lecture today, there was a question yesterday about this point that so the polarized GPDs contributes to the unpolarized process, and then Nicholas asked the question if what about the opposite case? So we are thinking about this process, and you have a GPD H and both unpolarized polarized GPDs, and then you take the square to get a cross section. So the unpolarized cross section goes like HH plus H tilde, H tilde. So in that sense, this is what I mean. So the unpolarized GPD, the polarized GPD also contributes to the unpolarized cross section. And for the polarized cross section, you have something like this. So in this sense, so it's a product of polarized and unpolarized GPDs. So in this sense, it also.
Does this structure, can you think about it in terms of parity?
Parity, yeah, I think so. Yeah. Yeah. So even if you have unpolarized scattering, so you have epsilon tensor here, but you square it, then epsilon tensor becomes 1. So that's why you get this extra term. And this one of the either amplitude or the compressed conjugate amplitude has to be polarized, and the partner should be unpolarized. So that was you can find the complete formula in this review article by Belitsky and Rajewski. It's very complicated formula, but you can find it here. All right, so today, my last lecture, I will be talking about form factors. I assure you that this is the simplest part of my lecture. So, not so much about the Cox and gluons. It's more like a general theory of form factor in hadron physics. So, all right, so let me start with the proton electromagnetic form factor, which is kind of probably more familiar to you. So we have electromagnetic current here, and then you have the proton states. It's all forward matrix element. You have P and P prime, and then you can parameterize this form factor in following way. So usually people just show the first two terms, F1 and F2, the Dirac and the Pauli form factor. But since this is a lecture, I added two more terms. So there is another term, F3, and something called the FA. Okay, so let me tell you the physical meaning of this. So this F1 is probably should be familiar with this. And if you take the zero momentum transfer, this should be 1. This should be normalized to the charge, electric charge of the proton, which is 1 in this case. So if this was a neutron, this should be 0. Now the second term is also very familiar. You should be familiar with this. If you take the value of zero momentum transfer, it should give you the G-2 of the proton. Okay, so that's the anomalous magnetic moment. And the third form factor, maybe you have never seen this, but this term is there if there is a parity and CP violations. Okay, so in QCD, this is 0, but it might be non-zero in the standard model if there is a CP violation. And in fact, this value at zero momentum transfer F3 of 0 is actually proportional to the electric dipole moment of the proton. Okay. Now the last term is even more exotic. I don't have a good explanation of this. This is something called anapole moment. Okay, so if you do this multiple expansion of the magnetic field, you have this monopole, dipole, quadrupole, octopole. But if there is a parity violation, there is something called anapole. Okay, so I don't have a good. You can look up the web, but so this is rarely discussed in our community. But some people interested in physics beyond the model, they may be interested. So here's the exercise. Derive the relation between F3 and EDN. Okay, so starting from this definition, why this F3 has the interpretation as EDN. Okay. Yeah, so this was originally I meant to be an exercise, but I realized that I gave you too many exercises. And this is a bit of a digression, so I give you an answer right away. So I'm not going to explain this to you. And so if you are interested, you can try to do it by yourself, and then check the solution is right or not. So well, otherwise, you can just read it. So this is basically the derivation. Okay, so at the end of the day, you should be able to find this. This is a non-relativistic potential. It's like a Hamiltonian, the potential in the Hamiltonian, which you can then you should get this familiar term. This is the electric field. This is the external electric field times the dipole moment. Okay, so you should be able to derive this formula. Well, this is the derivation, basically. The only non-trivial step is probably this. This may be non-trivial, but that's the for exercise. All right. Anyway, okay. So the form factor, theory of form factor, it's very convenient to look at this form factor in a particular frame. It's called the bright frame, or in other words, it's also called the brick wall frame. Meaning that so the proton is coming in this direction, and there is a infinitely hard brick wall, and so the proton bounces back 180 degrees and go to the opposite direction. So in this frame, you can parameterize the momentum of the incoming proton this way and the outgoing proton this way. The only difference is the sign of the three momentum. Okay, so this is the energy, and this is the three momentum. Incoming proton, outgoing proton, you have a minus sign. Yeah, that's this. So you can always choose to work in this frame. And in this frame, you can work out the spinor product. So if you have this gamma matrix here, this sigma mu rho here, and you have spinors, but you know the spinor, explicit form of a spinor, right? So you can do that. For example, this product of u bar gamma mu u looks like this in this particular frame. Okay. So I'm just using the explicit form of the spinor in these formulas. And so this is a zero component, and this is a spatial component. And they can work out a similar way. This is a scalar product of the spinors like this one. So if you do this expansion, then you have some nice physical interpretation of the electric and magnetic form factor. So if you look at the zero component, so it's a time component of this electromagnetic form, then, okay, so this is an exercise. Show that in this particular frame, this is J0 matrix element is given by this particular linear combination of F1 and F2. And this, we call it the electric form factor, GE, which was shown by George in his lectures. Now, if you look at the spatial components of this electromagnetic current, then you have a different combination of F1 and F2. It's just a sum of them. And this is called magnetic form factor, yes, which is usually written as a GM of the T momentum transfer. So, so these two definition is tied to the bright frame. Okay. And in this frame, you define the radius, the quote unquote radius of the hadron. So let's start with the electric form factor, GE, which is a particular combination of F1 and F2 in the bright frame. And you do the Fourier transform of this, and the Fourier transform is this rho of R. R is a three-dimensional coordinate. Now you're going to interpret this rho as the electric charge density inside a proton. And this R is a radial coordinate from the center of the proton towards the radial directions. Now, you are interested in the small momentum region. So let's say this K is very small, then I can expand this exponential in power series like this one. And then, so this one term just gives a constant, and the second term vanishes because of the rotational symmetry. And the last term, okay, the third term, there is this R squared times K squared. The K squared is just T. So if I take the derivative of G with respect to T, then I pick up this third term, and that's you have this r squared times rho, and that defines the radius of the proton. Okay. And okay, so this relation was shown in George's lecture, but I'm going to explain why you have this factor of 6 here. And that's simply because the average of cosine square phi is 1/3. Okay. That's why you have the 1/6 here. So this is a definition of proton charge radius that everybody is talking about. But I have to also give you a caveat. This is just one definition of radius. Okay, radius of hadron is an ambiguous quantity. Okay, you can define radius in infinitely many ways, to be honest. And this is just one definition. But once everybody agrees on the definition, and if there is a well-defined way of measuring this radius, then that's fine. So that's how it works. And this particular definition, from the way it was derived, it's clear that this definition is uniquely tied to the bright frame. And I know some people don't like this definition, and they propose other definition of radius. There's some theoretical problem with this bright frame, but I don't want to go into that direction. So there's lots of discussion, or lots of debate about what is the radius of the hadron. But this is the most popular and most well accepted definition. Maybe some people object. All right, so you can actually measure this in the experiments. This was first done by this gentleman in 1950s, Robert Hofstadter. And this is basically the elastic scattering from the proton. So you have electron-proton elastic scattering, and you know this famous Rosenbluth formula. So by measuring this angular dependence, so theta is related to the momentum transfer T, and then you can get this F1 and F2, this in this particular combination by measuring this theta dependence, and you can separately determine this F1 and F2 from this measurement. This is called Rosenbluth separation. And from that data, experimental data, they have determined the first extraction of the proton radius back in 1950s, which is around 0.8 Fermi. All right, so it's quite remarkable that people are still doing these experiments, and lots of experiments actually doing this. So even after 17 years, 70 years, there are many experiments going on, and if there are future experiments, even future experiments planned. And you should look at so this is a compilation of the existing data and the future experiments. And you should look at the x-axis here. This is a q square, which is t, which is a momentum transfer. And these numbers like 10 to minus 3 and 10 to minus 4 is really small. So in order to get the radius, you have to take the derivative at the origin at q square equals to 0. So you need to approach to that small q square region, small t region. And the race is on, and all these collaborations are competing to get this q square equal to 0 regions. Okay, so this is how you determine this radius from the electron scattering, but you can also determine it in a completely different way. Okay, and I'm going to explain that by measuring the hydrogen atom spectrum. So this is hydrogen atoms. You have a proton and electron, and there is a Coulomb potential in between, right? So the Coulomb potential goes like E squared over 4 pi r. However, this formula basically assumes that this proton is a point-like object, which is not true because this proton has some special distribution of electric charge. So you have to correct this formula. So it's not just 1 over r, but you have to, so you can correct like this. So this GE is a Fourier transform of charge density. So this is how it looks like in the momentum space. So instead of 1 here, you put the GE here, okay? Now, since the potential is modified, the energy of the hydrogen is also modified. And so the potential, the difference of the potential between this and that, you can calculate it, and you can approximately relate this difference which is almost a delta function, and the coefficient is remarkably this charge radius squared. Okay. So you can use this delta V as a perturbation, and you include this perturbation in the first order perturbation theory, and you can calculate the energy shift due to this perturbation. And so this is a usual non-relativistic wave function of the electron, and then you do this from textbook. And if you do this calculation, then you get this energy shift is proportional to the charge radius squared. So if you can measure this energy shift very precisely, then you can get this R squared term here. And remarkably, what is interesting here is that you have this energy shift is proportional to the electron mass cubed. Okay. And so the idea is what if you replace this electron by muons, which is 200 times heavier than the electron. So if you replace this electron mass, the muon mass, then you gain a factor of 200 to the power of 3. That's 1 million, right? So you get the factor of 1 million enhancement of this energy level. So you can make a very precise measurement of this delta E. And from that, you can explain this, you can extract this charge radius. Somebody has a question here?
This is electrostatics, right? And you were defining the radius in the bright frame. So
you're asking the validity of this thing?
yeah,
Well,
interpretation of that as a radius.
Yeah, this is more like a classical picture. I interpret it as I think you understand your concern. This interpretation of the charge density is based on the bright frame. So whereas here I'm identifying this R with the R in the bright frame, the Fourier transform. I don't know. It looks plausible. I don't know. So in this formula, this B, when you write this, you are treating this proton as an infinitely heavy object, right? And bright frame is based on the idea that the proton is infinitely heavy. So there's a fixed position here. So in that sense, these pictures are consistent. But I understand your concern that there might be a small correction to that. But.
And also, if you are using the muon, now the center of mass is not always like in
Right. Yes. So there might be a further correction there. Yes. So that's very interesting. I don't know if this has been discussed, but yeah, I don't know. But anyway, this is a leading order correction. So you can measure this charge radius if you use the muonic hydrogen, and that was a reason of this so-called proton radius puzzle. So I think you're all very young, so you probably don't know that there used to be a puzzle. It's called the proton radius puzzle. So before 2010, the community has a consensus that the radius is something around 0.88 Fermi. And then there came experiments from this muonic hydrogen, where you can do the very precise measurement of the radius, and this was the result. It's different from the previous result by a large factor, and it's very precise. Look at this error bar; it's a very precise measurement. So that was, and then people were surprised because all the previous experiments from the electron scattering, and it was not consistent, right? So that was the proton radius puzzle, and then there was lots of excitement. But so they did people did the experiments, more precise experiments, and it seems to me that all the experiments from the electron scattering is converging towards the smaller radius. So nowadays, for example, this is an experimental data from JLab from 5 years ago. And you could from the electron scattering, and you can see this is the radius is 0.83, so it's in this region. So from an outsider like me, it seems to me that there's no puzzle anymore. It seems like the puzzle is converged. But it's very remarkable that if you look at the errors here, it's only 1% errors. So it's very precise measurement. And the people wants to go even more precise because all these are all future experiments.
In this radius, we are assuming the proton is a sphere. Or
No, no, what, I mean, you mean the spherical symmetric? Yes, yes. All right, so that was the proton. Okay, so much for the magnetic form factor. Now I move on to the gravitational form factor, which I already showed you a bit of it yesterday. So here, this is a Bell-Infante improved symmetric energy momentum tensor, which consists of the quark part and gluon parts. And if you take the forward matrix element, it just gives you 2 times P mu P nu. Okay, this is the usual parameterization. But I often hear the questions like, why isn't there a term proportional to G mu nu here? Right, because this is a 2 tensor, so in principle, you can have additional term here, which is proportional to G mu nu. And why is this term not there? It's a okay. So in order to answer that question, you have to go to the forward matrix element. Okay, so this is a forward matrix element, and this is the forward matrix element, and then you have 3 form factor A and B and D that I already talked to you yesterday. And there is no, okay, so there is G mu nu here, but it comes with together with this other terms here, and there's no G mu nu, extra G mu nu terms here. Because that will violate the conservation of the energy momentum tensor. So if there is an additional term here, G mu nu here, then you cannot this term violates the conservation law. So this term, there is also G mu nu here, but together, these 2 terms together is consistent with the conservation law. But if you have a G mu nu term, isolated G mu nu term here, that is not consistent with the conservation law. And if you take the forward limit, by continuity, there's no term proportional to G mu nu here. So that's why there's no G mu nu here. You have to think in terms of no forward matrix element and extrapolate to the forward matrix element. That's the only explanation I can think of, actually. Now, some people are interested in the trace of the energy momentum tensor because it's related to the anomaly, the scale anomaly, the trace anomaly of the QCD, which is related to the mass of the hadron. So that has something to do with the origin of the mass of ESC wants to address. So people are also interested in the trace of the energy momentum tensor, and their matrix element can be given in terms of the same form factor A and B and D. This particular, sometimes called the scalar form factor. Now, there are some general consequences of symmetry. So A form factor evaluated at 0, momentum transfer is 1. B is 0. I already explained this yesterday, but the value of D at 0 momentum transfer is unconstrained, and it's unknown at the moment. So its value, there are many model calculations of this, but value is basically unknown. And once you have this form factor, then you can define a bunch of new radius. I told you that you can define radius in infinitely many ways, and here are just some examples that I can think of from the top of my head. So I already told you it's charge radius, but one can define radius from a baryon number distribution inside a proton, or if you have an energy momentum tensor, different components, or different components gives you different definitions of radius. And people are interested in which radius is larger, smaller, and whether we can extract it from experiments. So that's a kind of hot topic right now. I'm also involved in that. So this was I already what I showed before in the previous slide is the total energy momentum tensor, but one can also decompose it into the quark part and the gluon part. You can define separately the form factor for the quark part and gluon part of the energy momentum tensor. Then once you do that, you basically get the same thing, except that you have now a subscript Q and G, which is quark and gluons. But there is additional form factor, which is commonly called the C bar. And this was absent in the total energy momentum tensor because the total energy momentum tensor is conserved. Whereas as soon as you decompose into the quark and gluons, then this is not conserved. And because it's not conserved, you can have an extra form factor here, which is proportional to G mu. Sorry, I'm using different notation, eta mu, but it's basically G mu. And this form factor has to vanish. It's there, but it has to vanish if you can once you go back to the total energy momentum tensor. So the sum of C bar over all the flavors and gluons must be 0 because the total energy momentum is conserved. But once you switch to quark, if you look at the components, then this is 0 by energy momentum conservation. All right, so here's one slide about the connection between GPD and the form factor. So the electromagnetic form factor that I showed you, F1 and F2, is just a first moment of the GPD-H and GPD-E. Okay. Now, one caveat here is that so GPD is a function of H and skewness and T, but if you take the moment in X, the skewness dependence disappears. And think about why this is the case. Well, the usual explanation is that if you integrate over X, you get a local operator. But the skewness is a momentum transfer in the particular direction, right? So, but once you shrink it to the local operator, there is no particular direction. So that's why yet the dependence has to vanish. But then that doesn't explain why you have a skewness dependence in the second moment of the GPD, which is energy momentum tensor. And so here, the energy momentum tensor, you have this term. And remember, the skewness is proportional to the delta plus. So here, this term goes like skewness, quadratic in skewness, even though this T plus plus is a local operator. Okay, so the real reason you don't have this eta dependence here is, I think it's because of the time reversal invariance, which I don't want to go into, but it's also, yeah, so I think that's a bottom line. And then, okay, so coming back to this energy momentum tensor, you have A and B, but yes, and then this last term, which has a different Lorentz gamma matrix structure. This is just one unit matrix here, but you can use a Gordon identity to write this term and combine this together with the A and B. So A and B are shifted by this last term. Remember, you know, the Gordon identity. If you use that, you get this linear combination A plus skewness squared times D, B minus skewness squared times D. And these are the objects which is related to the second moment of the GPDs. Okay, so I think when I talked about the G-sum rule yesterday, I was only showing the, where is it? Yeah, so in this relation, I said skewness equal to 0 and T equals 0. So that was this, I showed this. But now I'm generalizing to finite T and finite skewness. And then this is the, then you have an extra term, which is proportional to the function. Yeah, so this is a more general relation, which also depends on skewness and T. So in principle, if you can measure this GPD from experiments very precisely, you should be able to extract this T function. And this T function is very interesting because this is a very nice physical interpretation as pressure distribution inside the proton. So remember, this D term is associated with the special component of the energy momentum tensor. So this Tij, so this Ij runs from 1 to 3. So I'm using the three-dimensional notation. And I remind you, this D evaluated at T equals 0 is a conserved charge of the nucleons. And so there is no renormalization group evolution for this quantity. And it's in this sense, it's similar to the magnetic moment of the proton. So it's a fundamental constant of nature, fundamental constant of the proton. Now, the nice thing is that once you do the Fourier transform of this D with respect to T, the momentum transfer to go to the coordinate space, then there is a nice physical interpretation as the quote-unquote pressure distribution inside the nucleons, first advocated by Maxim Polyakov. And the reason is that the spatial, usually if you consider some continuous medium, the spatial component of the energy momentum tensor is related to the pressure distribution of the medium. You can make a connection. So here's a relation between this D and pressure as a function of radial coordinate, or you can invert this relation and express this D as a spatial integration of the pressures. Now, there's a widespread conjecture in the community that all the stable hadrons must have negative Ds. Okay, so this is a conjecture. There's no proof, and there is even a counterexample. But it's interesting. It's coming from the stability argument. So in order for the hadron to be stable, then the integrated pressure must be negative. Otherwise, the partons fly apart. But I warn you that all this is just an analogy, okay? Because the proton is not really a continuous medium. It's a quantum system with zero ground state of the ground state of this QCD. So you shouldn't take this word pressure too literally. So, but nevertheless, this is, I think, an interesting analogy. All right, so this picture George already showed. This is the first extraction of this pressure distribution from the JLab experiment using DVCS, and this is the pressure times R square. And this is so as a function of the distance from the center of the proton and small radius region, there is a positive. This is like a hard core, it's a repulsive core. And then in the outward region, there is a negative region. So that's force that try to shrink the system. And that is resisted by this hard core. And that's how the proton is stabilized. So that's a very nice explanation why proton is stable. And here we also repeated the same exercise for the nucleus. This was for the proton, but you can also do the similar analysis for the nucleus using some model calculation. And so this is a proton that you show, that is you see on the left. This curve, this is a deuteron, this is a triton, this is a helium-4, and so on. Okay? And you see this pressure distribution near the core is negative, which is different from this picture. So starting from deuteron already, all the nucleus we studied, they have negative pressure near the core of the proton. I don't know how to interpret this stuff in terms of stability. And we are not the only ones who find this behavior. There's people of Adam Fries and Wim Cousin, and there's a group of Stony Brook. The author is sitting in the back. And so they also computed the, I think, helium or deuteron pressure. So it would be very interesting if we can measure this in experiments. Okay. All right, so I was talking about proton GAF, gravitational form factor, but one can also talk about the pion gravitational form factor, and that's kind of interesting. So the difference is that the pion is a spin 0, and that means that you have only 2 gravitational form factor. Okay, before for the proton, you have 3, A and B and D, and for the pion, you have 0, so you only have 2 form factor. Now, what is very remarkable is that I told you that this D is not a constraint, right? It can be any, it can be anything, but for the proton, and we don't know this value, but for the pion, remarkably, we know its value. If the Koch mass is set to 0. Okay, so there is a statement that in the chiral limit of QCD, so chiral limit means that the Koch mass is 0, so the pion mass is also 0. And in this limit, D has to be -1. You can take it as a theory. So this should be an exact statement. So I walk you through the proof of this in full generality. So here's the proof. So start from this matrix element of P and P prime. And now take the limit of this P prime going to 0. Okay, so all the components of P prime goes to 0. Let's look at this soft limit. So the outgoing pion has 0 energy, very soft. Now, you plugged it into this definition. So P prime is 0. So capital P, the average is just P over 2, right? And this momentum transfer P prime is 0. So delta is just minus P, right? And delta square is P squared, and P squared is 0 because I'm thinking of the chiral limit. Okay, pion is massless in this ideal world. So the right-hand side simplifies a lot, and basically what you find is this linear combination of A0 and D0 because T0. Okay, very simple. So that is the right-hand side, and on the left-hand side, this is a non-perturbative matrix element, but I can use a very powerful tool, which is known as the soft pion theory. So this dates back to more than 50 years, even before the QCD. People came up with this soft pion theorem, like people like Weinberg and Coleman, all these people are talking about this soft pion theorem. So the theorem is that if you have matrix element with pion external states, and this pion moment, if you take the limit that this pion momentum goes to 0, then it is proportional to this commutator between the whatever operator you have here with the generator of the chiral rotation, which is given by this operator. Okay. So this is a generator of SU2, SU3 chiral rotation. This is a theory. Okay, I will give you a proof in the next slide, but let's take it for granted for the moment. And once you accept, then you can immediately conclude that this commutator is 0, because the energy momentum tensor is invariant under the chiral rotation. There's no chiral charge. So that's why this. So the left-hand side is also 0. And then, so that means if I go back, so this linear combination A plus D is 0, which means that A is minus D, and since A is 1, D has to be minus 1. Okay, so this is a rigorous result just from the consideration of pion as a number called some more boson of broken chiral symmetry, and this is the constant. So the value of D for pion is completely fixed by the chiral symmetry. But of course, in the real world, there is a correction because pion mass is not exactly 0, and then you have an extra term which is proportional to the pi and pi squared. But in any case, this is a proof of this statement. So here's just one slide, derivation of the soft pion theorem, which was crucial when deriving this relation. So this first relation. So here's a proof, which is just 5 lines. So we start with the matrix element of axial vector operator J5 mu with the external pion state. You have this F pi. You can think of it as a definition of F pi. Okay. So this is a pion decay constant. This is a definition of decay constant F pi. Now you take the derivative of both sides. You take the divergence. You have a divergence of axial current. On the right-hand side, the derivative acts on this exponential and brings down the P. So P squared is M pi squared. So this means that you can interpret this derivative of divergence of axial current as the pion field, the pion interpolating field. Okay, so this combination of the operator acts as the pion interpolating field. It can excite the pion single particle states with the correct normalization. Now, then you use the LSZ reduction formula. So you consider the generic scattering amplitude where you have pion in the final state, and take this, then you have, this is the usual reduction formula, except that the pion field, so this is a pion field, which I can replace with this effective interpolating field. So I have a derivative, I have a divergence of the axial current here, and then I can pull out this divergence outside this time ordering procedure, okay? Now, when you pull out this divergence outside this time ordering, you have to worry about the cross term. So this derivative can act on this time ordering, right? So the time ordering gives you the theta function in time, and this derivative, when you try to pull it outside this matrix element, this derivative acts on the time of theta function and gives you a delta function. So that's the second term here, but first term is just the usual naive. So derivative is taken outside this matrix element. So this is a formula, and then at this I'm gonna soft pion theorem works, and then I can drop all the so this is a derivative, so this is like a p, so I can get rid of this derivative here, and I can also get rid of this derivative here because pion momentum is 0. The only term that remains is m pi squared times this extra term here, and that gives you the soft pion theory. Okay, very. So this is a one slide derivation of. Okay, so the bottom line is that d of the pion is completely fixed by the chiral symmetry, which is remarkable. This is not the case for the protons. I think I'm going too fast. I have only few slides left, so probably I finish earlier. So my last point is the question. It's very interesting. Can we measure the gravitational form factor in experiments? There's lots of computation. You can compute calculation of gravitational form factor in models and lattice QCD, but at the end of the day, we want to measure it in experiments. And I think JLab and ESC experiments are ideally suited for that purpose. So let me tell you why it is so difficult to measure the gravitational form factor. So the history is actually long. So the first time the gravitational form factor was introduced was in the 60s. And at that time, so the history is almost as long, well, it's not as long as electromagnetic form factor, but it's pretty old. Right? But it didn't receive any particularly strong attention from the community. Right? So far less attention from the electromagnetic form factor. But in my opinion, that's not because they are less interesting or less important. There's one obvious reason: we cannot measure it directly. That's the only. In my opinion, that's the only. And the electromagnetic form factor, that's so popular because people can measure it. But this gravitational form factor contains even rich, in my opinion, is even richer physics than the electromagnetic form factor because there are many components, but it received very few attentions from the community over 60 years. And the reason, so why is it so difficult to measure it? So suppose you do an experiment, right? So you want to measure this gravitational form factor, so you do the scattering experiments. Some arbitrary two particles, and then you exchange the graviton here. So the cross section goes like this. So d sigma dt goes like some constant times s squared. So this s is the center mass energy. So you might think that this is very promising because it's a rapidly rising cross section. If you increase energy, it's very rapidly rising. But this is an illusion. Because if you look at this constant here, this Gn, it's a capital G, is a Newton constant, okay? And this Newton constant, I remind you that is proportional, basically, is 1 over the Planck mass squared, okay? So you have G squared here, which means that this cross section is proportional to the 1 over the Planck mass to the power of 4. And the Planck mass is 10 to the 19 GeV. So you get a suppression factor by what's 10 to the minus 76. So that's a gigantic suppression, right? So whatever you have here is ESC energy is 100 GeV, LHC's energy is 10 GeV, sorry, 10 TeV, or you can think about 100 TeV. It doesn't matter because of this enormous suppression here. So that tells you how difficult it is to measure this. You basically need a Planck energy collider. You do the scattering experiments at the Planck energy in order to overcome this enormous suppression. Okay, so that's why That's why people didn't think about it. It's almost like a scientific fantasy. So the direct measurement is impossible from this argument, but there are some clever people out there, theorists, and they came up with indirect ways to measure this form factor. So let me tell you a little bit of that. So the idea is very simple. So I want spin 2 particle, right? So this graviton has a spin 2, but so we don't have it. But then what about? But we don't have a spin 2 particle, but maybe we can mimic a spin 2 particle if you have 2 spin 1 particles, like 2 photons, 2 gluons. So the idea is very simple. 1 plus 1 is 2. Yes, that's it. So if you look at this DVCS that I told you before, you see 2 photons. So there is a voucher photon and outgoing photon. So you have 2 photons. So you can mimic the spin 2 state. So these 2 photons can realize the spin 2 state. So maybe you can interpret this process as one graviton exchange from between these 2 photon system and protons. So this system has to be to some part sensitive to the gravitational form factor. So that's the idea. Or you can think of other processes like phi meson production, J psi, upsilon. This is a bound state of SS bar, CC bar, and BB bar. And these heavy mesons are sensitive to the gluon degrees of freedom in the protons, or the lowest order, we should start with the 2 gluon exchange like this. And if you have 2 gluons, this mathematical formula 1 plus 1 is 2 should be operative. So this process should be sensitive to the gluon part of the gravitational form factor. So that's it's a very naive but very interesting ideas. But however, life is not so easy because it turns in reality the 2 photon, the 2 gluon state can couple to operators with arbitrary speeds. I explained to you that in DIS, leading twist, infinitely many operators contributing to the cross section at the leading twist, right? So there are twist 2 operators, there are infinitely many twist 2 operators with different spins. So you have spin 2, spin 4, spin 6, they're all twist 2, and they all contribute to these processes. So the question is, how can you isolate the spin 2 part of that? That's energy momentum tensor. So there are infinitely many operators contributing, but you want to keep the contribution from one operator, which is the energy momentum tensor, and that's a challenge. So I'm not going to give you a review of that, but I'm just saying that this is a very active area of research now. So and it will be interesting because you can measure these processes at the JLab and the Electron-Ion collider. So I'm not going into the details, but let me just show you that my most recent paper is in this direction. So this is a proposal to measure the pion gravitational form factor at the Electron-Ion collider and JLab. The idea is to use the so-called Sullivan process. You might have heard of this. So it's basically the process in which this proton first emits pi plus and splits into pi plus and neutron, and this pi plus interacts with this photon, and then you introduce this phi meson or J psi near the threshold regions. And the claim is that this process is sensitive to the gluon part of the gravitational form factor. So this is yes, and this can be measured at JLab and the Electron-Ion collider. So I'm doing this kind of things in recent years. So actually, this is the end of this is the last slide. Your question?
Yeah, so for how any J psi that you measure would be coming from this channel, or what is like, I guess, like the experimental signature of the phi that you're talking.
Yeah, so the experimental signature is that J psi decays into the lepton pairs.
Yeah.
So you have to reconstruct to the J psi mass. You should reconstruct the invariant mass of the E plus E minus or mu plus mu minus, and that's so you have to identify all the particles in the
Okay.
final state.
Okay, and the pipe.
So it's a very challenging measurement. It's not, I don't know if it's I don't know how experimenters think about this, but it's basically you have to reconstruct all the final states. But this is actually the people usually use to calculate the measure the pion electromagnetic form factor.
Okay.
So in that case, there is no meson here. You just have pi plus, and that gives you. So instead of d mu nu, you have electromagnetic form factor of the pion, and this is how the JLab people measure the pion electromagnetic form factor. And this process is a generalization of that. So here we are trying to measure the gravitational form. So that's basically it. But okay, but yes, but if there is a remaining time, maybe you can ask a question about some of the exercises if you want help. And
Start by thanking Yoshitaka. Maybe.
okay. Tomorrow, so today is my last day, but in the afternoon I'll be sitting in one of the offices there. So if you have questions, need help to solve the exercises I gave you, you can come to me and talk.
Other questions to ask Yoshitaka, presence of everybody. Okay, go.
So when you were showing the pressure as a function of A, or rather as a different curves corresponding to different A. So for the large nuclei, how do you understand the oscillating behavior?
Yeah, that's I have a cartoon of how this nucleus looks like, and this is a very weird structure. So it might be an artifact of this model. I'm using the model called the Skull model, and to construct this large nucleus. And I don't have the cartoon here, but it has some peculiar structure. So it might be an artifact of that. But you see this large oscillation just because I'm multiplying by R squared. So if you go to the large R region, this is enormously amplified. So that's why it's a bit exaggerated because of this R square factor. But it depends. This structure, oscillating structure, has to do with the structure, spatial density of nucleus near the edge of the nucleus. So that's, and then I don't know if I don't have a simple explanation, but I tend to think of it as an edge effect, the skin effect.
Have you calculated this pressure, internal pressure for some other particles like light mesons or resonances?
Personally, I haven't done that, but I think there are many papers, flurry of papers coming out in the last several years, and people have computed the pressure of pion, rho meson, delta resonances, and here this is a nucleus, all sorts of patterns.
Could you explain a little more about why the stability of the proton will mean d term being lower than 0?
Well, I recommend. No, I don't have a simple explanation, but so this D you can write it in terms of this way, right? So it's average pressure inside a proton, and this has to be negative. Otherwise, these components just fly apart to infinity. So that's a very just an intuitive explanation. I think this also comes from the analogy with the ordinary matters, the macroscopic continuous medium, classical medium. If you talk about the stability of these classical systems, I think this is a condition. There was a review paper by Polyakov and Schweitzer, which is very nice, and they describe all these stability argument based on its pressure on the term. Otherwise, I don't have much explanation other than this. There is a calculation by Shandong Ji and collaborator. They show that the D is positive for the hydrogen atom. There might be other systems with the positive D, but so far all the hadrons, for the hadrons, lots of calculation models and artists, and they all find the negative. I don't know why.
Question. When you showed the slide of elastic scattering 70 years, you showed a ratio between GE over JD. So then we can see a flat close to 1, but then when Q squared is greater than 10⁻3, we have some change. I'm wondering if one of these quantities constant or if what is JD?
Sorry, I don't know. Yeah, what is this?
JD,
Sorry, I didn't look at that.
because I think that the JD increase, we have the decay of this rate.
I don't know. You can look at this reference here. This is a review by the experimentalists.
I feel like they would say that it's consistent with the uncertainties on the lower side.
Because it's flat.
Right. So in general, the form factor decays with increasing Q squared, but yeah, right. So this denominator might also be a function of Q squared. So I don't know. You look at this reference.
So when you showed the plot of the proton radius and they had these two different values back in 2010, it's all the list of all the experimental results.
Yeah.
So did they go back and these 2010 experiments on the right? Yeah, 2011. So is there a reason why they see? I mean, the error. If we trust the error bars, or do they not trust it?
I don't. I'm not an expert of that. I think Jan Barner was here at Stony Brook.
Oh.
Is he still here? Yeah, he's a faculty at Stony Brook, right? So yeah, you can ask him. I don't know the question. You have to approach Q square. You have to extrapolate to the Q square equals 0, and then of course it's a very forward scattering, right? So Q square 0 means that the electron has no basically 0 angle. There is no deflection angle, so it's very forward region. It's very difficult to measure it. So that's the yeah, I don't know. That's experimental limitation at the time, probably.
And which of the many different radii calculations match this 0.83 the closest?
You mean the model calculation?
Yeah, there was, charge radius, baryon radius, all of those different ones. Do they all get close, or does one get close?
I don't know. I don't think model calculation has this precision. I mean, you can calculate charge radius in whatever models you have, but I don't even know if even lattice can reach this precision. This is precise. Get to the 1% precision. That's I'm not sure. So experiment is going ahead of model stuff, I think.
Right. Very good. Let's thank Yoshitaka once again. He's still here today, so don't just jump on him now. Let him have lunch. Are you going to be here after lunch?
Yeah.
Okay, he's gonna be here after lunch. Okay, so now don't start queuing here because we need to beat the crowd at Simon Center. Let's have lunch, and then we'll probably come a little bit earlier. So whatever questions you want to have solutions for homework problems, show your solutions to Yoshitaka, hopefully, and check whether it's correct. Let's probably meet shortly before 1, and then we can do it.
And on the WhatsApp, I put the information of the train and the bus. Looks like the bus may be more convenient. And you can self-organize. There are a couple cars. There's a one-way car, or you can do the bus. And again, that's optional, but you know, it's a nice place to wander around and